Have you ever wondered what's really going on when someone does math? I mean, are they just inventing these incredibly complex games with made-up rules? Or are they actually discovering a hidden reality that's been there all along? It's a huge question, and today we're going to dive right into it.
So, here's the central tension, the big idea for today. For ages, people have argued about this. On one hand, you have the idea that mathematicians are like novelists, just creating these elaborate fictional worlds that happen to have very consistent rules. But on the other hand, what if they're more like astronomers, discovering these timeless truths that were already out there, just waiting for us to find them? Well, it turns out, the answer might be a really mind-bending yes to both.
All right, so let's start with that first perspective. This idea that math is, at its core, just a really sophisticated game of make-believe.
This view has a name. It's called fictionalism, and it basically argues that things like the number 3 or a perfect circle, they don't actually exist out there in the world. They're more like fictional characters in a story. So when we say 2 plus 2 equals 4, a fictionalist would argue that what we're really saying is something like, according to the story of arithmetic, 2 plus 2 equals 4. It's an incredibly useful and powerful story for sure, but it's still just a story.
From this angle, a mathematician isn't discovering some eternal truth. They're just a really, really dedicated player who is meticulously figuring out all the possible moves and outcomes based on the rules of the game that they, or somebody else, set up in the first place. It's its own little self-contained universe of logic.
But, and this is a big but, this is where things get complicated. Because if math is just a game, it's a bizarrely effective one, right? I mean, it lets us send rockets to Mars. It predicts how quantum particles behave. And that incredible power comes from its absolute precision.
So this raises a huge question. How can a simple game of make-believe be so unreasonably good at describing our reality? And if you want your game to be that powerful, what does its rulebook even need to look like? It can't have any ambiguity, right? No loopholes allowed.
And this brings us to a concept called categoricity. You can think of it as the philosophical gold standard for a mathematical rulebook. A theory is categorical if its rules are so perfectly, so precisely defined that there is only one possible way to play the game. Every single valid version of the game board will have the exact same fundamental structure. There's no room for interpretation.
Think of it this way. Standard logic, what we call first-order logic, is kind of like telling someone to build a house. You might get a tiny cabin or a mansion or a bungalow. They're all technically houses, but they're different versions of the game. But second-order logic, that's like giving them a complete architectural blueprint. It is so precise that it just locks in the structure, guaranteeing that everyone, no matter what, builds the exact same house.
And this is where our game of Pretence takes this astonishing turn and starts to build a bridge to something that looks an awful lot like reality.
I mean, really think about that for a second. If you write a set of rules for a pretend world and those rules are so flawless, so categorical, that they can only describe one single unique structure, well, is it still pretend at that point? Or have you accidentally written a blueprint for something real?
This leads us to this absolutely wild idea called plenitudinous Platonism. This view says that any mathematical story you can tell that is perfectly consistent, that doesn't contradict itself, isn't just a story. It necessarily corresponds to a real abstract pattern or structure that actually exists out there in some abstract realm.
And this quote just nails the core idea. It doesn't matter what the mathematician thinks they're doing. By creating a perfectly consistent game, they have inadvertently discovered a piece of an abstract reality. The act of pure, precise invention becomes an act of discovery, whether they even realize it or not.
Okay, I know this is getting pretty abstract, so let's bring it back down to earth with something really simple. A map and the territory it might be describing.
So, first up, the Pretence. Imagine you sit down to create a fantasy world for a game. You draw a map of a cool dungeon, making up rooms and corridors as you go. You're fully aware that you're just pretending. This dungeon is a complete work of fiction. That's fictionalism in action.
But now, let's see how this evolves. Imagine you get obsessed with making this map perfect. You define every single angle, every hallway's length, every spatial relationship so perfectly that anyone who follows your rules would have to build the exact same dungeon. There are zero loopholes. Your map has just become a categorical blueprint.
And here's the punchline.
According to Planitinous Platonism, because your map is so consistent and so unique, it's not just a map of a fictional place anymore. It's a perfect description of a pattern that genuinely exists in this abstract multiverse of all possible logical structures. Your game of pretending to draw a map has accidentally led you to discover a real territory.
So what does all this mean? Well, it suggests that maybe, just maybe, we've been asking the wrong question all along. Maybe math isn't about fictional objects or real objects. Maybe it's about something else entirely.
And this brings us to structuralism. This is the idea that mathematics is basically the science of patterns. It doesn't really matter if you call a spot on the number line 3, or use Roman numerals. What matters is its relationship to 2 and 4, the pattern itself, the structure. In the end, both the fictionalist playing a game and the Platonist discovering a world are really just exploring these structures.
And what's so fascinating about all this is that our confidence in these patterns, it often comes later. It's not like we always know at the start whether we've stumbled upon a truly fundamental pattern or just an interesting but maybe flawed game.
And this idea is backed up by some pretty cool concepts. Take extrinsic evidence, for example. The thinking is we believe in a set of rules not just because they feel intuitively right, but because they lead to really powerful and useful results. A game that helps us build bridges starts to feel a lot more real. We also see it in how definitions get refined over time. We're constantly stretching our concepts to fix errors and get closer and closer to that perfect underlying pattern we were trying to capture all along.
So here's the beautiful journey we've been on. We start out just playing a game, pretending objects and rules exist. But as we demand more and more precision from that game, we end up cornering ourselves into describing a unique, unchanging structure. And in doing that, our act of pure invention transforms, maybe without us even noticing, into an act of pure discovery.
Which leaves us with this final question to chew on. When a mathematician sits down with a pencil and paper, are they just drawing a map of their own imagination? Or are they, through the sheer force of logic and precision, revealing the contours of a territory that has been there all along?